Deep in the outer reaches of our solar system, orbiting the ring giant Saturn, there exists a moon so bizarre, so utterly alien, that when scientists first saw its detailed images, they struggled to explain what they were looking at. This is not your typical round, cratered world. This is something that looks like it was pulled from the depths of an ocean, a sponge-like object tumbling chaotically through the void of space. And here's what makes it even stranger. This moon is electrically charged, firing beams of particles into the darkness of space, creating an invisible bridge between itself and anything that dares to approach. This is Hyperion, and its story is one of the most fascinating tales in planetary science. To understand why Hyperion is so special, we first need to travel back in time, back to the year 1848, when two astronomers working independently on opposite sides of the Atlantic Ocean made the same discovery within days of each other. William Cranchbond, working at the Harvard College Observatory in Massachusetts, and William Lassell, observing from his private observatory in Liverpool, England, both spotted a tiny point of light moving against the backdrop of stars near Saturn. This was the first moon to be discovered simultaneously by two different observers, and it would be named after the titan of Greek mythology, Hyperion, the god of watchfulness and observation. A fitting name, as it turned out, for a moon that would watch over Saturn for billions of years. But in 1848, Hyperion was nothing more than a dot of light. No one could have imagined what secrets it held. For over a century, it remained a mystery, just another small moon in Saturn's growing family of satellites. Astronomers noted that its brightness seemed to vary unpredictably, suggesting it was tumbling in some unusual way, but the details remained frustratingly out of reach. Everything changed in the late 20th century when humanity sent its first robotic emissaries to the outer solar system. The Voyager spacecraft, those twin ambassadors of Earth, swept past Saturn in the early 1980s and gave us our first close look at Hyperion. What they revealed was startling. This was no ordinary moon. Its surface was pockmarked with deep, sharp-edged craters, giving it an appearance unlike anything else in the solar system. But even Voyager's cameras could only capture so much detail from their brief flybys. The real revelation came with Cassini. The Cassini-Huygens mission, launched in 1997 and arriving at Saturn in 2004, would spend 13 years exploring the Saturn system in unprecedented detail. And when Cassini turned its instruments toward Hyperion, it unveiled a world that defied explanation. The images that came back to Earth showed a moon that looked almost organic, like a piece of coral or a natural sponge. Its surface was covered with countless craters, but these weren't like the craters on our own moon or on Mars. These were deep, cylindrical pits with dark material at the bottom, giving Hyperion the appearance of something porous, something you could squeeze water out of. The reason for this bizarre appearance lies in Hyperion's extremely low density. If you could somehow weigh Hyperion and measure its volume, which scientists have done through careful analysis of spacecraft trajectories, you would find that this moon is barely denser than water ice. In fact, about 40% of Hyperion's interior is empty space. It is essentially a loosely packed rubble pile, a collection of icy debris held together by its own weak gravity. This porosity explains why its craters look so strange. When an asteroid or comet strikes most solid bodies, the impact creates a bowl-shaped depression as material is ejected outward. But when something hits Hyperion, the porous surface acts more like a sponge. The impacting object punches straight down, compressing the loose material beneath it rather than blasting it outward. The result is those distinctive, deep, steep-walled craters that give Hyperion its unique honeycomb appearance. But the strangeness doesn't stop there. Hyperion's rotation is unlike anything else in our solar system. Most moons, including our own, rotate in a predictable, synchronized way. They keep one face pointed toward their parent planet at all times, a phenomenon called tidal locking. The moon always shows the same face to Earth. Jupiter's large moons do the same. Even most of Saturn's other moons follow this pattern, but not Hyperion. Hyperion tumbles. Its rotation is chaotic in the mathematical sense of the word. This doesn't mean it's random or disordered in a colloquial way. It means that its rotation is governed by chaotic dynamics, where tiny changes in initial conditions lead to dramatically different outcomes over time. If you were standing on Hyperion's surface, assuming you could find stable footing on that spongy terrain, you would see Saturn rise and set in completely unpredictable directions. Some days, it might appear in what you thought was north. Other days, it would rise from a completely different point on the horizon. The length of your day would change constantly. You could never predict where the sun would be in your sky from one rotation to the next. This chaotic tumbling happens because of Hyperion's irregular shape and its orbital relationship with Titan, Saturn's largest moon. Titan is massive, more than 50 times larger than Hyperion, and its gravitational pull constantly tugs at the smaller moon. Combined with Hyperion's elongated, potato-like shape and its eccentric orbit, these gravitational interactions create a situation where stable, predictable rotation is mathematically impossible. Hyperion is the only known moon in our solar system that exhibits this true chaotic rotation, making it a natural laboratory for studying chaos theory in celestial mechanics. Now, let's talk about what makes Hyperion truly extraordinary: its electrical nature. When Cassini flew past Hyperion in September 2005, something unexpected happened. The spacecraft's instruments detected a sudden change in the surrounding space environment. Electrons were flowing from Hyperion toward Cassini, creating an electrical current between the moon and the spacecraft. This was the first direct evidence that Hyperion was electrically charged. To understand why this happens, we need to think about the environment in which Hyperion exists. Saturn is surrounded by a complex magnetic field, the second largest in our solar system after Jupiter's. This magnetic field traps charged particles from the solar wind, creating radiation belts similar to Earth's Van Allen belts, but far more extensive. These particles, electrons and ions, constantly bombard everything within Saturn's magnetosphere, including its moons. When these charged particles strike a moon's surface, they can knock loose other particles, a process called sputtering. On most moons, this creates a kind of equilibrium. Particles arrive, particles leave, and the surface remains electrically neutral on average. But Hyperion is different. Its highly porous, insulating surface, made of water ice mixed with dark organic compounds, doesn't conduct electricity well. This means that when charged particles hit certain areas of Hyperion, those areas can build up a static charge that doesn't easily dissipate. Think of it like shuffling your feet across a carpet on a dry winter day. You build up a static charge because the carpet is an insulator, and that charge stays on your body until you touch something conductive like a metal doorknob and discharge it all at once with a spark. Hyperion is doing something similar, but on a cosmic scale. Its surface builds up negative charge in some areas, while other areas become positively charged. The difference in charge can reach several hundred volts. When Cassini passed within about 2,000 kilometers of Hyperion, it flew through what scientists call a particle beam, a stream of electrons flowing away from the moon's surface. This beam is essentially Hyperion discharging its built-up static electricity into space. The spacecraft itself became part of the circuit, momentarily connecting different charged regions and allowing current to flow. This discovery has profound implications for future exploration. If a spacecraft, or someday astronauts, were to land on Hyperion, they would need to account for this electrical charging. The surface could be at a potential of several hundred volts relative to the surrounding space, enough to cause problems with sensitive electronics or to create unexpected sparks during landing operations. It's a reminder that space exploration involves challenges we don't always anticipate. But Hyperion's electrical behavior isn't just a hazard. It's a window into understanding how airless bodies throughout the solar system interact with their space environment. The same processes that charge Hyperion occur on asteroids, on other moons, and even on the surfaces of planets without significant atmospheres. By studying Hyperion, we learn about the electrical nature of space itself. Let's zoom out for a moment and consider Hyperion's place in the grand architecture of the Saturn system. Saturn has at least 146 known moons, ranging from Titan, larger than the planet Mercury, down to tiny moonlets just a few hundred meters across embedded in the rings. Hyperion occupies a middle ground, large enough to have been discovered in the 19th century, but small enough to have avoided the gravitational forces that would have shaped it into a sphere. Hyperion orbits Saturn at an average distance of about 1.5 million kilometers, taking approximately 21 days to complete one orbit. Its path lies between the orbits of Titan and Iapetus, two of Saturn's most famous moons. This orbital neighborhood is significant. Hyperion and Titan are locked in what astronomers call a 4:3 orbital resonance, meaning that for every 4 orbits Hyperion completes, Titan completes exactly 3. This gravitational relationship helps maintain the stability of Hyperion's orbit over millions of years, even as Titan's gravity contributes to its chaotic rotation. The proximity to Titan raises interesting questions about Hyperion's origin. Some scientists believe that Hyperion might be a fragment of a larger moon that was destroyed by a catastrophic collision billions of years ago. The Saturn system has seen its share of violence over its history, with moons colliding, breaking apart, and sometimes reforming. Hyperion's unusual shape and low density would be consistent with it being a surviving piece of a larger body, a cosmic survivor clinging to existence in the shadow of its giant neighbor. Others suggest that Hyperion might have formed in place, accreting from the debris disk that surrounded Saturn early in its history. In this scenario, Hyperion's porosity would be primordial, a relic of the gentle accumulation of icy particles that never experienced enough heat or pressure to compact in a solid rock. Either way, Hyperion preserves a record of conditions in the early solar system, frozen in time for 4.5 billion years. The dark material that fills Hyperion's craters adds another layer to the mystery. Spectroscopic analysis by Cassini revealed that this material contains organic compounds, complex molecules built around carbon atoms. These aren't signs of life, at least not in any sense we would recognize. Instead, they're probably the result of chemical reactions involving simple molecules like methane and ammonia, driven by ultraviolet radiation from the sun and charged particles from Saturn's magnetosphere. Similar dark, organic-rich material is found on other moons and objects throughout the outer solar system. Iapetus, Saturn's two-faced moon, has one hemisphere coated in this dark stuff. The nucleus of Comet 67P, visited by the Rosetta spacecraft, was covered in organic compounds. These observations suggest that the outer solar system is rich in the raw materials for organic chemistry, the building blocks that could, under the right conditions, lead to the emergence of life. Hyperion's organics are locked away in a frozen, radiation-bathed environment that seems utterly hostile to life as we know it. But they remind us that the universe is constantly conducting chemistry experiments, mixing and matching molecules across billions of years and trillions of kilometers. Somewhere, somehow, some of those experiments might have yielded results more interesting than frozen organic sludge. Let's return to that electric charge and explore what it means for the larger story of the solar system. Hyperion is small, distant, and seemingly insignificant on the grand scale of things. It's easy to overlook, but its electrical behavior connects it to processes happening throughout the cosmos. Everywhere in the solar system, surfaces are being bombarded by radiation and charged particles. On bodies with atmospheres, like Earth or Titan, this bombardment is largely absorbed before reaching the ground. Our atmosphere protects us, but on airless worlds, the Moon, Mercury, asteroids, most moons of the outer planets, the surface takes the full force of the space environment. This creates a complex electrical landscape, with surfaces charging and discharging in response to sunlight, shadow, and the local plasma environment. On the Moon, for example, astronauts reported that fine lunar dust seemed to levitate and cling to their equipment in unexpected ways. This was caused by electrostatic charging, the same basic phenomenon that gives Hyperion its particle beam, just manifesting differently. Understanding these processes is crucial for designing equipment and habitats for future human exploration of the Moon, asteroids, and beyond. Hyperion's extreme example, with its highly insulating surface and powerful charging, serves as a kind of natural stress test for our models of surface charging in space. If we can understand what's happening on Hyperion, we're better equipped to predict and manage electrical effects on other destinations throughout the solar system. The Cassini mission that revealed so much about Hyperion came to an end in September 2017, when the spacecraft was deliberately plunged into Saturn's atmosphere. This was done to prevent any possibility of the spacecraft eventually crashing into one of Saturn's potentially habitable moons, like Enceladus, and contaminating it with Earth microbes. Cassini's grand finale was a fitting end to one of the most successful planetary missions in history, but it also means that our eyes and ears at Saturn are now silent. We currently have no spacecraft operating in the Saturn system, and none are planned to arrive for years, possibly decades. The data Cassini collected is still being analyzed, and there's undoubtedly more to learn about Hyperion from the terabytes of information stored in scientific archives around the world. But for now, new discoveries will have to wait. This gives us time to appreciate what we do know and to wonder about what remains hidden. Every world in our solar system has secrets. Even a small, sponge-like moon tumbling chaotically beyond 1 billion kilometers from the sun has managed to surprise us. It challenges our assumptions about what moons should look like, how they should rotate, and how they interact with their environment. Hyperion reminds us that the universe is stranger than we imagine, stranger perhaps than we can imagine. We build models and theories based on what we've observed, But nature constantly finds ways to exceed our expectations. A moon that looks like bath sponge and shoots electricity into space sounds like something from science fiction. Yet there it is, real and documented. A small world going about its business in orbit around Saturn. What else is out there, waiting to be discovered? What other worlds will challenge our understanding when we finally get a close look at them? The outer solar system is full of moons we've barely glimpsed, small, icy bodies that have never been visited by spacecraft, known only as points of light in telescope images. Each one could hold surprises as profound as Hyperion's chaotic rotation or electric charge. And beyond our solar system, around other stars, there are countless moons we can't even detect yet. If the moons of Saturn are this diverse and unexpected, what marvels must orbit the gas giants of distant planetary systems? The universe has had billions of years to create wonders, and we've only begun to explore. The story of Hyperion is also a story about human curiosity and ingenuity. It took 2 centuries from its discovery to its close-up exploration. In that time, we went from peering through telescopes to sending robotic ambassadors across the solar system. We developed the technology to keep a spacecraft operating for nearly 20 years in the harsh environment of deep space. We figured out how to interpret data from instruments measuring particles and fields that are invisible to our eyes. Each discovery about Hyperion, its porosity, its chaotic rotation, its electric charge, was the result of clever engineering and patient science. Real people devoted their careers to understanding this small world. Proposals were written, funding was secured, instruments were designed and built, spacecraft were launched and navigated, data was collected and analyzed, papers were published, and our understanding of the universe expanded just a little bit more. This process continues today, even without active missions at Saturn. Scientists are still working with Cassini data, still making new discoveries, still refining our models of how the outer solar system works. And engineers and mission planners are developing concepts for future missions that might one day return to Saturn and its moons. Some have proposed missions that would specifically target the smaller moons, the ones overshadowed by famous destinations like Titan and Enceladus. A dedicated mission to Hyperion could answer questions that Cassini's brief flybys could only raise. What is the internal structure of this porous moon? How does the electrical charging vary across its surface and over time? What can its organic compounds tell us about chemistry in the early solar system? Such a mission would be technically challenging and expensive. The outer solar system is far away, requiring years of travel time, even with optimal trajectories. Power is limited. Solar panels produce little electricity so far from the sun, forcing reliance on radioactive power sources. Communication delays mean the spacecraft must be largely autonomous. But these challenges are not insurmountable. We've overcome them before, and we'll overcome them again when the scientific questions are compelling enough. The questions Hyperion raises are certainly compelling. This strange little moon touches on fundamental issues in planetary science: the formation and evolution of small bodies, the dynamics of rotation and orbital mechanics, the interaction between surfaces and space environments, the distribution of organic compounds in the solar system. Understanding Hyperion better would improve our understanding of all these areas. But perhaps the greatest value of studying Hyperion is harder to quantify. It's the sheer wonder of discovering that the universe contains such bizarre objects. It's the reminder that no matter how much we think we know, there's always something new and unexpected waiting to be found. It's the inspiration that comes from looking at a picture of a sponge-shaped moon and asking, how did that happen? What else is out there? These are the questions that drive exploration, that motivate scientists to spend decades on a single mission, that inspire children to dream of becoming astronauts or astronomers. Hyperion might be small and distant, but its strangeness captures the imagination in a way that more familiar worlds don't always achieve. So, what have we learned from this small moon orbiting in Saturn's shadow? We've learned that moons don't have to be round. Gravity tends to pull large bodies into spheres, but smaller ones can retain irregular shapes, recording the history of collisions and accumulation that formed them. Hyperion's potato-like form is a window into processes that shaped the early solar system. We've learned that rotation can be unpredictable. The dance of gravity between Hyperion, Saturn, and Titan creates a situation where stable rotation is impossible, leading to chaotic tumbling that has continued for billions of years. This is chaos theory written in the motion of a world. We've learned that surfaces in space can become electrically charged, and that this charging can have dramatic effects. Hyperion's particle beam is an extreme example of a phenomenon that occurs throughout the solar system, with implications for future exploration. We've learned that organic compounds are common in the outer solar system, mixed into the ices of moons and comets, perhaps delivered to the early Earth by impacting objects, seeding our planet with the materials that eventually led to life. And we've learned, once again, that the universe rewards those who look closely. Every world has a story to tell, if we have the patience and ingenuity to listen. Hyperion continues its eternal tumble around Saturn, its surface charging and discharging, its deep craters collecting dark organic dust. It knows nothing of the small machines that briefly visited from a pale blue far toward the inner solar system. It knows nothing of the scientists who have devoted years to understanding its mysteries. It simply exists, as it has for billions of years, a strange and wonderful object in the cosmos. One day, perhaps, we'll return. Perhaps a new spacecraft will orbit Hyperion, mapping every crater and measuring every electrical field. Perhaps rovers will land on its porous surface, testing the ice and analyzing the organics. Perhaps humans will eventually visit, standing on that bizarre terrain and watching Saturn hang huge in an ever-shifting sky. Until then, we have our images and our data, our models and our theories. We have the knowledge that such a place exists, that the solar system contains wonders beyond our everyday experience. We have Hyperion, Saturn's strange, electric, tumbling moon, a reminder of how much there is still to explore. The outer solar system stretches vast and dark beyond Hyperion. Saturn's other moons each hold their own secrets. The ice giants Uranus and Neptune, visited only briefly by Voyager 2 decades ago, orbit even farther out with their own families of moons barely glimpsed. The Kuiper Belt extends beyond Neptune, home to Pluto and countless smaller icy worlds. And beyond that, the Oort cloud, a sphere of comets at the very edge of the sun's gravitational influence, marks the boundary between our solar system and interstellar space. All of these regions await exploration. All of them likely contain surprises as profound as anything Hyperion has shown us. The story of our solar system is far from complete. We've explored a tiny fraction of what's out there, and every new mission rewrites what we thought we knew. Hyperion has taught us to expect the unexpected. It's a lesson worth remembering as we plan the next stages of exploration. Whatever we find out there, whether it's strange moons, complex chemistry, or phenomena we can't even imagine yet, we should approach it with humility and wonder. The universe is vast, ancient, and endlessly creative. We're just beginning to understand its masterpieces. And so we return to where we began, to that small, tumbling world, spinning unpredictably in the cold darkness beyond the asteroid belt, charged with electricity, pockmarked with craters that look like they were carved by some cosmic sculptor with a taste for the surreal. But let us pause here and consider something profound. When you look up at the night sky, Saturn is visible to the naked eye. It appears as a steady, yellowish point of light, unremarkable among the thousands of stars scattered across the darkness. Ancient humans saw that same point of light. The Babylonians tracked its slow movement across the sky. The Greeks named it after Kronos, the father of Zeus. For thousands of years, humanity watched Saturn without any idea of the wonders that orbited around it. Now think about this. Within that tiny point of light, invisible to your eyes, there's a moon the size of a small city, shaped like a sponge, tumbling chaotically through space, shooting beams of electrons into the void. Hyperion has been there all along, doing exactly what it does now, for billions of years before the first human ever looked up and wondered about the lights in the sky. It will continue long after our civilization has risen, fallen, and been forgotten. There's something humbling about that thought. We are brief visitors in a universe that operates on timescales we can barely comprehend. Hyperion formed when the solar system was young, perhaps from the debris of a catastrophic collision, perhaps from the gentle accumulation of icy particles in the disk of material that surrounded the newborn Saturn. Either way, it has been tumbling ever since, through the age when Earth was a molten ball of rock, through the era when the first life emerged in our oceans, through the rise and fall of the dinosaurs, through the entire history of human civilization. And it noticed none of it. Hyperion simply exists, indifferent to the drama playing out on a small rocky planet closer to the sun. Its craters record the history of impacts from comets and asteroids. Its surface chemistry tells a story of radiation and particle bombardment spanning eons. Its chaotic rotation is a mathematical dance that has played out for longer than multicellular life has existed on Earth. When Cassini flew past Hyperion and detected that stream of electrons, when it captured those stunning images of the honeycomb surface, it was gathering information that had waited 4.5 billion years to be collected. Think about the patience required. Not human patience, but cosmic patience. The universe creates its wonders and then waits, for eons if necessary, for someone or something to come along and appreciate them. We were that someone. For a brief moment in 2005, a machine built by human hands, carrying instruments designed by human minds, passed close enough to Hyperion to see it clearly and measure its electric breath. That moment lasted only hours, but it connected us to a story billions of years in the making. This is what space exploration really means. It's not just about collecting data or advancing technology or even preparing for future human settlement of other worlds. It's about reaching out across the void and touching something ancient and strange, about adding our brief chapter to a story that began long before us and will continue long after. Hyperion will keep tumbling. Its surface will keep charging and discharging. Impacts will continue to carve new craters into its porous face. Titan's gravity will continue to pull at it, maintaining that chaotic dance. The dark organic material will continue to accumulate in the bottoms of those strange cylindrical pits. Nothing we do will change any of that, but we will have been there. We will have seen it. We will have understood, at least a little bit, what Hyperion is and how it works. That knowledge is now part of human heritage, preserved in scientific papers and databases, taught in classrooms, shared in videos like this one. A small piece of the universe has become part of us. And perhaps that's the real magic of exploration. Every world we visit, every moon we photograph, every comet we analyze, they all become part of the human story. We expand ourselves by reaching outward. We grow by discovering. Hyperion was unknown to us for most of human history, just another faint point of light near Saturn. Now it has a name, a shape, a story. It has been woven into the tapestry of human knowledge. The same process is happening right now, all across the solar system and beyond. Astronomers are discovering new moons around the giant planets. Space telescopes are detecting exoplanets around distant stars. Future missions are being planned to destinations we've never visited. With each discovery, the universe becomes a little less mysterious and a little more familiar, though never less wonderful. What will we find next? Perhaps a moon with a subsurface ocean teeming with microbial life. Perhaps an asteroid rich in metals that could fuel future space industries. Perhaps a planet around another star with an atmosphere containing signs of biological activity. The possibilities stretch before us like an endless ocean, and we have only dipped our toes in the water. Hyperion reminds us that even the small, overlooked objects in our cosmic neighborhood can hold profound surprises. If a tiny, irregularly shaped moon can exhibit chaotic rotation, electrical charging, and organic chemistry, phenomena that no one predicted before we looked closely, what might we find when we examine the countless other small bodies scattered throughout the solar system? There are asteroids we've never visited, comets we've never sampled, moons of Uranus and Neptune that remain little more than dots in our telescopes. Each one is a potential Hyperion, a world with secrets waiting to be revealed. The solar system is not empty space with a few planets scattered through it. It's a rich, complex environment filled with objects of every size and composition, each one a natural laboratory conducting experiments in physics, chemistry, and dynamics. Our job, as curious beings on one small planet, is to explore as much of it as we can. We do this through robotic spacecraft, through telescopes on the ground, and in orbit, through theoretical models and computer simulations. We do it because we want to understand our place in the universe, because we're driven by a need to know what's out there, because exploration is woven into the fabric of human nature. Hyperion embodies all of these motivations. It's a scientific puzzle. Understanding its formation, dynamics, and surface processes advances our knowledge of planetary science. It's a technical challenge. Flying a spacecraft to Saturn and collecting data from its moons required decades of engineering development. It's a source of wonder. Looking at those images of the sponge-like surface, we can't help but marvel at the strangeness of the cosmos. And it's a teacher. Hyperion teaches us that nature doesn't follow our expectations. We thought moons should be round, but Hyperion is shaped like a potato. We thought moons should rotate predictably, but Hyperion tumbles chaotically. We thought moons should be electrically neutral, but Hyperion fires particle beams into space. Each of these surprises force scientists to reconsider their models, to ask new questions, to dig deeper into the physics of how worlds work. This is the scientific process in action, not a smooth march toward truth, but a constant dialogue between expectation and observation, between theory and evidence. Hyperion threw curveballs at us, and we adjusted our swing. That's how science advances, one surprise at a time. The future of Hyperion exploration remains uncertain. No missions are currently planned to return to this strange moon. Budget constraints, competing priorities, and the sheer difficulty of outer solar system exploration mean that Hyperion may not see another spacecraft visitor for decades. But the data from Cassini continues to yield insights. Scientists are still analyzing those images, still interpreting those particle measurements, still building models to explain what we observed. And when we do return to Saturn, as we inevitably will, driven by our insatiable curiosity, Hyperion will be waiting. It will still be tumbling, still charging, still collecting organic compounds in its craters. It will have aged a few more decades, but on cosmic timescales, that's nothing. Hyperion measures time in billions of years. A few decades is less than the blink of an eye. Perhaps future explorers will land on Hyperion's surface, directly sampling its strange ice and organic materials. Perhaps they'll drill into its porous interior, discovering what lies beneath the honeycomb surface. Perhaps they'll set up monitoring stations to track its electrical behavior over time, watching how it responds to changes in Saturn's magnetosphere and solar activity. Or perhaps we'll discover something that makes Hyperion even more interesting, a subsurface pocket of liquid water, evidence of recent geological activity, complex organic molecules that hint at prebiotic chemistry. The universe has a way of exceeding our expectations. We go expecting one thing and find another. That's what makes exploration worthwhile. For now, we have our memories of Cassini's encounters. We have the images of that bizarre, pockmarked surface. We have the data showing electrons streaming from the moon into space. We have the mathematical models describing its chaotic rotation. These are the gifts Hyperion has given us, and they're considerable. But more than the data, more than the images, what Hyperion has really given us is a sense of wonder. It's reminded us that the universe is full of things we never imagined, that nature is more creative than our theories allow, that there's always something new to discover if we're willing to look. That sense of wonder is perhaps the most valuable thing we can take from the exploration of space. It keeps us curious. It keeps us humble. It keeps us reaching outward, building spacecraft and telescopes, sending probes to distant worlds, dreaming of the day when humans might follow. Hyperion is out there right now. As you listen to these words, tumbling through the darkness around Saturn, electrons are flowing from its surface into space. Solar ultraviolet light is driving chemical reactions in its organic-rich craters. Titan's gravity is tugging at it, maintaining its chaotic dance. It doesn't know we exist. It doesn't care about our theories or our missions or our dreams. But in some small way, we've become connected to it. We've seen it closely, understood it partially, added it to the catalog of known wonders in our solar system. That connection, fragile and one-sided as it is, enriches us. Every child who sees an image of Hyperion and asks, "What is that?" is participating in the grand human project of exploration. Every student who learns about chaotic rotation or surface charging is building on centuries of scientific work. Every scientist who analyzes Cassini data is contributing to a legacy that stretches back to those first telescopes pointed at Saturn in the 17th century. We are all part of this story. Hyperion is part of this story, and the story is far from over. Out there in the darkness, beyond the orbit of Jupiter, past the rings of Saturn, a sponge-shaped moon continues its eternal tumble. It has done so for eons. It will continue for eons more. And perhaps someday, when humans have spread beyond Earth and established themselves throughout the solar system, someone will stand on Hyperion's surface and look up at Saturn's rings arcing across the sky. They'll think about the Cassini spacecraft that first revealed this moon's secrets. They'll think about the scientists who puzzled over its chaotic rotation and electrical charge. They'll think about all the steps, all the discoveries, all the dreams that led from those first observations in 1848 to their footprints in the ancient ice. And they'll realize that they're standing on a world that once seemed impossibly remote, impossibly strange, impossibly out of reach, now made familiar, made accessible, made part of the human domain. That's the promise of exploration. That's why we do it. That's what Hyperion, in its silent, tumbling way, reminds us of every time we look towards Saturn. The universe is waiting. All we have to do is reach out and touch it, and we will.